Hello and welcome to the first edition of Calculus at Home. Bored? Need something to do? Well, here's your solution. Today we will be looking at differentiation theorems and functional analysis. I will try and just cover the most basics of both of these, enough so that you can keep up with the course. If you find any of the sections particularly difficult, I suggest pausing and maybe watching them again. I will be emailing out some problems following this. Alright, so let's get into it. Alrighty, so the first theorem, which you may have seen before, is the intermediate value theorem. The intermediate value theorem actually doesn't use calculus at all. Basically just tells us that if we have a continuous function between a and b, and f of a and f of b are not the same, then the function must take every value between f of a and f of b at some point between a and b. This is actually not as complicated as it sounds. And I will go ahead and draw you guys a function. Let's get out our pen here. And let's use red. Okay. So if we've got a graph that looks like this, it's about as good as it's going to get. And let's say this is the point A, and this is the point B. And we have a function, and it goes like this. And you'll notice that this function is continuous. I did not pick up my pen at all between A and B. And basically what this theorem says is that from this point here to this point here, f of x, the function, is going to take every single value between here and here. So we're going to go all the way down. So I pick any value. Let's say I want to pick this value right here. I can see I've got it right here and here and here. So it's really quite obvious. If the function is continuous, you're not actually going to miss any values. Okay. So let's have a look at an AP problem. So a conveyor belt has the ability to go forwards and backwards. During the time interval 0 to 60 seconds, the velocity function of the belt, v of t, measured in inches per second, is a continuous function. So this is the word that you really want to look for. Once it talks about continuous functions, you're usually going to be using one of the theorems. So just keep that in mind. The table below shows values of this function at selected times. For t between 0 and 60, what is the minimum number of times that the belt must have stopped? So we're looking for the number of times that the belt must have stopped. So the key word here is stopped. So right now we've got a sentence. We need to turn it into something that we know about. So let's see. So we've got v of t, and we're looking for when it stops. So if something stops, then it must not be moving, right? So its velocity must be equal to 0. And remember, the intermediate value theorem says that between any two points, f of t, it will take every single value as long as the function is continuous. And we have the function is continuous. So what we're looking for is values that go between positive and negative. So we see here, we go from 8 to negative 3, which means we must take the value 0. So there's one place where the velocity must have stopped. Here we have minus 3 to minus 3, so it doesn't tell us anything. Here we have minus 3 to 0. Well, here it just outright tells us that the function stops here. So that's another one. And then we go 0 to negative 5, so that's no use. Then negative 5 to negative 2, so that's no use. So from this chart alone, we can tell that this conveyor belt has stopped 2 times at an absolute minimum. Great. Okay, so let's move on to another AP problem. So the function f and g are continuous. The continuous function h is given by h of x is equal to negative x times g of f of x. So first of all, let's underline the fact that f and g are continuous. That's really important. That means that we're going to be using one of our theorems. And this function looks pretty difficult, but really it's just going to be a matter of plugging things in. So whenever you see a table like this, generally you're not going to be doing a whole lot with, let's say, the power rule or whatnot. You're mostly just going to be plugging values in. So the table below gives selected values of the functions, explain why there must be a value of t for between 1 and 7 such that h of t is equal to negative 10. Alright, so let's have a look here. So what we want to do is, first of all, we want to check the function at h of 1, because right here it says we're looking between 1 and 7, so that is the key. These this number 3 and this number 5 are used to trick us, but we will not be fooled. So h of 1 is equal to, well, now as we plugged in 1 for x, negative x is simply just going to be negative 1. We're multiplying by g of f of x. So we're looking at g of f of 1. This is equal to negative 1 times g of, well, let's have a look and find out what f of 1 is. So we simply look where x equals 1, we go down, f of 1 is 5. Okay. Now we need to find out what g of 5 is. So here we go. Here's 5, and we're going for g this time, so we're going to go down 2. That's negative 1. So we have negative 1 times negative 1. The two negatives make a positive, so h of 1 is simply equal to 1. Okay. Now we need to check h of 7. So we're going to do exactly the same thing. So h of 7 is equal to negative 7 times g of f of 7, which is equal to negative 7 times g of, well, let's have a look what f of 7 is. So when x equals 7, then f of 7 is 1. So now we've got negative 7 times, well, let's find out what g of 1 is. So here's 1, go down, and it is 2. So negative 7 times 2 is equal to negative 14. Now remember, f and g are continuous, and also h is continuous. Therefore, we know between 1 and negative 14 we must take every single value. And look at that. H of t must be equal to negative 10 somewhere because of the intermediate value theorem. So IVT says there must exist, so there exists a t such that h of t is equal to negative 10. So the most important thing about this is we're trying to find these two values of h, and then we can use the intermediate value theorem to show that negative 10 will exist because it is between 1 and negative 14. Excellent. Let's move on to the next one. Alright, now for the big one. This is the mean value theorem. You actually must be able to state this by name in the AP calculus test, and plus it's also really convenient. It actually makes our lives a lot easier. So the mean value theorem is actually very similar to the intermediate value theorem, except this time we're going to be talking about derivatives. So if a function f is continuous on the interval a, b, and differentiable on the interval a, b, that just means you're able to take the derivative, then there exists some c that's between a and b such that f prime of c, so the derivative of f at c, must be equal to the average slope between these 2 points a and b. So this basically says if you have a continuous function and you know the average slope is m between points A and B, then there must be a point C between A and B where the slope is equal to m. Another way to see this is that the secant line for A and B must be parallel to the tangent line of some point C between A and B. So I'll go ahead and draw this, and hopefully it'll be a lot more clear. So again, let me make my graph. Really hard to draw straight lines on this pad, but I am trying. And let's say our function looks like this. Okay, so let's say this is the point A, and this is the point B. And then we have between f of A and f of B, so here's f of A and f of B, we know that the slope between these 2 points is just this line here. And our mean value theorem tells us that the slope at some point on this line, on this curve, sorry, the derivative must be the same as this slope here. So let's have a look around, see if we can find it. That looks about right. So if you look at that, slope at this point exactly is the same as the slope between A and B. And you'll also see that these two lines are parallel. All right, very good. So let's see if we can go ahead and apply this. So before I move on, it's just really important that we remember the formula f of B minus f of A over B minus A. This is the average slope between f of A and f of B. We need to know this formula because this is what's going to enable us to solve problems with the mean value theorem. And really quick, let's also go over Rolle's theorem. So Rolle's theorem is just a special version of the mean value theorem. So now what we're going to do is we're going to say that f of A and f of B are actually the same point, or they hold the same value. Then the average slope is 0 on AB, therefore there must exist a point C such that the derivative is equal to 0. So what this looks like is, let's say, well, let's go ahead and draw, let's go ahead and draw our graph. I'm going to do a much better job than that. There we go. Erase full ink on slide. Let's try that one more time. So, there we go, and there we go. So let's say the function starts here, and it'll go like this, like this, like this, like this, and ends here. This basically says that if these 2 points have the same f value, so basically the same y value, then the average slope between these 2 points is 0, because remember, f of B minus f of A over B minus A is our average slope. But if f of B and f of A are the same thing, it would be like, let's say, 5 minus 5 or 7 minus 7, it's going to be equal to 0. That's going to be equal to 0 divided by B minus A, and 0 divided by anything is just equal to 0. And you'll be able to see that there are actually a few points where the derivative is 0. Here's a point, you can see the derivative is 0. Here's a point, the derivative is 0. Here's a point, derivative is 0. And here's a point where the derivative is 0. Okay, so show that Rolle's theorem holds between the roots of f of x equal to 12x minus x cubed. So there's actually quite a lot of information in here. First we're talking about Rolle's theorem, then we're given a function, but we're also told to find the roots. So if you remember, the roots of the function are where the function passed the x axis. So that must mean that the y value of those points is 0. So if we set this whole function equal to 0, we'll be able to find the roots. So 0 is equal to 12x minus x cubed. Now in order to solve this, we're actually going to have to factor this. So 0 is equal to, well, what can we factor out of this? We can factor an x. So we get x times 12 minus x squared. And I have a lot of trouble when my x is negative. But let's see if we can try and solve this first without having to make any huge changes. So by the zero product property, something times 0 is always 0. So if we make x equal to 0, the whole thing equals 0, and then we found one of our roots. So we already know x is equal to 0, which comes from right here. And we can apply the same thing with the stuff in the brackets. So we will have that 0 is equal to 12 minus x squared. Now I want to solve for x and get x by itself. So, like I said before, I don't really like negative x squared, so I'm actually going to plus x squared to both sides. So I get x squared is equal to 12, and then to get x by itself, I can square root both sides, but always remember when you square root both sides, you have to take the positive and the negative root. And I can simplify this radical just a little bit more. So this is equal to plus or minus, well, 12 is just the same as 3 times 4. And the square root of 4 is 2, so this is equal to plus or minus 2 times the square root of 3. Alright, so there are our 3 roots. We've got 0 and plus or minus is 2 times root 3. Okay, now let's go ahead and get a different pen color for this next bit. Let's use green. Okay. So what we want to find is that the derivative is 0, because that's what Rolle's theorem tells us about. It tells us about the derivative being 0 between our roots. So we want to find out that there's one between negative 2 root 3 and 0, and between 0 and positive 2 root 3. So let's go ahead and take the derivative. So f prime of x is equal to 12 minus 3x squared. Now, once again, we're trying to find out when the derivative is equal to 0. So let's make this equal to 0, and we get 0 is equal to 12 minus 3x squared. And similarly to the last time, like over here when we had 0 is equal to 12 minus x squared, we are going to add the x squared term to both sides. So we get the x squared by itself, and we also get rid of that pesky negative sign. Okay, now I'm going to divide both sides by 3, and I get x squared is equal to 4, and I square root both sides, and remember you have to take the plus or minus, so x is equal to plus or minus, and the square root of 4 is just 2. Now, this may not feel like we're done, but in fact we are. Because look at this, we found out that the derivative is equal to 0 at negative 2 and positive 2. Well, negative 2 is between negative 2 root 3 and 0. So if we drew this on a number line, like this, the first thing you would see is negative 2 root 3. And then between those two, you would see negative 2. And the reason negative 2 root 3 is further along the number line is because root 3 is bigger than 1. And then here we'll have 0. Then after that would come 2. Then after that would become 2 root 3. And we have shown that the derivative is 0 between the roots. So between these two roots, we have a derivative equal to 0, and between these two roots, we have a derivative equal to 0. And that's it. We're done. Okay, let's see if we can get all this ink off this slide. Let's see. Okay. I guess not. Okay, well that's fine. I will just talk through what's already been annotated. So, a ball is bobbing along in the ocean and traveling in a straight line due to the waves. Its velocity over a 60-second period is a differentiable function given at 6-second intervals in the following table. Excellent. So we see that the function is differentiable, which is good because remember the mean value theorem, we talk about functions being differentiable. So if you see that word differentiable, that should be a big buzzer word that says that we might have to use the mean value theorem. So here we are at 6-second intervals in the following table. What is the minimum number of times the ball is stopped? So once again, remember, the ball stopping must mean v of t is equal to 0. We're already talking about v of t, so we're going to be using that theorem we just learned, the intermediate value theorem, the one before the mean value theorem. So again, we're just looking to see where it goes from positive to negative or negative to positive. So 5 and 2, both positive, that's not going to help us. 2 and negative 2. Oh, well that means that we must cross 0, so that's one time. Then here we have 0, so that's another time. And between negative 1 and 3, we must pass 0. And between 4 and negative 2, we must pass 0. So if you count these up, you got 1, 2, 3, 4 times. So the minimum times the ball stopped must be 4. So now it's asking between what two times must the ball have no acceleration? Well, if you remember, the derivative of velocity, so v prime of t, is equal to acceleration. So that's a of t. And we're trying to find out when there's no acceleration. So that must be where a of t is equal to 0. So what we're looking for is a point where the acceleration must be equal to 0. So let's see if we can use the mean value theorem or Rolle's theorem. Well, remember Rolle's theorem tells us that if you have 2 points the same on the graph, the derivative must be 0 between them. So if we can find two of the same velocities, we know that the acceleration must be equal to 0. So just as a reminder with the mean value theorem, we have v of some value b minus v of a over b minus a. And remember, v of b and v of a must be the same if we're using Rolle's theorem, so we would have the whole thing equal to 0. So all we're doing is looking on this graph here and trying to find two of the same values. So here we got negative 2, and here we got negative 2. So we know that between 12 seconds and 54 seconds, somewhere there must be acceleration equal to 0. So that's asking, so the question is actually asking between which two times. So we would simply write t equals 12, comma, t is equal to 54. And that's it. Okay, unfortunately we tried to record this before, but the sound came out really, really bad. So we've ended up getting all this ink on the slide, and I can't seem to find a good way to get it off. So I will try and talk through this really quick. So let f be a twice differentiable function. Select values of f and f prime are given in the table below, and let h be the function given by h of x is equal to f of x. Show that there must be a value c between 1 and 4 such that the second derivative at c is equal to negative 10. So we know that we're going to have to start taking some derivatives. In fact, we're going to have to take two derivatives. So first of all, let's find out what the derivative of h is. So the derivative of h, well, here we're going to be using the chain rule because see, we have a function inside a function. It's the same function, but we still have to apply the chain rule. So remember, derivative of the outside, leave the inside by itself, then derivative of the inside. So h prime of x is equal to f prime of f of x times f prime of x. And we're interested at the values between 1 and 4. So we're actually going to take the, we're actually just going to leave the first derivative and not go ahead and take the second derivative because the mean value theorem will hopefully answer this for us. So if we can find that the average velocity between 4 and 1 is -10, then we know that there must be some value c between 1 and 4 where it is also -10. So let's go ahead and plug in 4. So h prime of 4 is equal to f prime of f of 4 times f prime of 4. And f of 4, well, let's look in the table. Let's look x equal to 4, then we're looking at f of 4. Oh, that's actually just 2. So f of 4 is equal to 2, and f prime of 4, well, let's have a look here. We're get x equals 4, then f prime, oh, that's 7. Okay, good. So we have f prime of 2 times 7, and then f prime of 2, well, let's look here. We got 2, and then f prime of 2 is equal to -4. So here we have -4 times 7, which is equal to -28. Right, so now we're just going to do exactly the same thing with h prime of 1. So h prime of 1 is equal to f prime of f of 1 times f prime of 1. Once again, we're just plugging in. So this is equal to f prime of, well, let's have a look what f of 1 is. So here's 1, f of 1 is equal to 3. So f of 1 equals 3, so f prime of 3, and then we're timesing by f prime of 1. So let's have a look, see what that is. We have f prime of 1 equal to -1. Okay, so now we have f prime of 3 times -1. So now we just need to find out what f prime of 3 is. So once again, we look, here's x equals 3, and f prime of 3 is -2. So we finally get -2 times -1, 2 negatives make a positive, so this is equal to 2. Now we just go ahead and plug these things in. So we're going to use that average slope formula. I will write it one more time. You must remember this. So the average formula, and I'll put it in terms of h's, says that the average slope is h. Let's just go ahead and use f's. It might make our lives a little bit easier. It's kind of confusing here because we're talking about the second derivative. So let me just go ahead and write this in terms of f's. So f of b minus f a over b minus a. But here, of course, we're talking about the second derivative, so we're going to relate the first derivative to the second derivative. So we've got h prime of 4 minus h prime of 1 over 4 minus 1. Or we have 4 minus 1 because those are our two x values we're looking at. They're given right here. So h prime of 4 is equal to -28, and h prime of 1 is equal to -2. Is equal to 2, but we are minusing, so we have -28 minus 2, and then 4 minus 1 is 3, and this is equal to -30 over 3, which is equal to -10. And look at that. That's exactly what we're looking for. I have to admit, this was a really, really hard problem. This is about as hard as it gets on the AP test, if you ask me. They do not expect that everyone, even people who make a perfect score, to get this kind of problem right, but I just want to expose you to it now so that you've got a fighting chance for when it comes around. Okay, I think we're going to skip over this problem. Here, it's just basically trying to use the mean value theorem to find something on a calculator. We will go ahead and look at this some other time. Okay, great. And that is the first part, which was on mean value theorems. If you like, you can go have a tea break or whatever you'd like to do before we start on functional analysis. Okay, functional analysis. So in functional analysis, we are analyzing the structure of a function using both algebra and calculus. So here is a function. My pen ready here. Let's use a different color than red. Let's use purple. Why not? So in functional analysis, we are trying to describe different parts of the function by looking at derivatives. So when the derivative is equal to 0, so remember, derivative is the same as slope, so we're looking for when the slope is 0, which is the flat line. We have a point here, and we have a point here. Now you may notice that these are special parts of the graph. Here, it seems to be the maximum of this little area, and here seems to be the minimum of this little area. We call these 2 points critical points. And that is where the derivative is equal to 0. And we call this right here a relative maximum. We call this right here a relative minimum. And you can see between critical points, the function's either going up or it's going down. And when you pass a critical point, you're often, not always, but you're often changing between positive and negative. Okay, so now what we're going to do is we're actually going to look at a different kind of point, which is called the inflection point. So let's get out, let's do green this time. We are looking for where the second derivative is equal to 0. So what that means is we're going to look at different slopes, and we're going to look where the slope stops changing. Okay, so you see here, we're pretty steep and we're pretty uphill. So the slope here is probably about, I don't know, let's say 5. So let's say f prime of x is about 5. And here we're getting less and less steep, then here, let's say the slope's maybe 2 or so, so f prime of x is equal to about 2, then all of a sudden, right here it's about 1, then 0, then, oh, look at that, we're going down now, so right here, f prime of x is probably about -2. And then right here, it looks like it's about the steepest downhill we have, where f prime's maybe -3, then all of a sudden we're getting less steep on the downhill, less steep, and then we're getting more and more steep uphill. So the slope went from 5, 4, 3, 2, 1, 0, -1, -2, -3, then all of a sudden we go turn around, -2, -1, 0, 1, 2, 3, 4, 5, and so on and so forth. That point when we're turning around from the slope going less and less steep until it gets negative, we're going to call this point the inflection point. And it's more often than not halfway between the relative maximum and relative minimum. Okay. So we say f of x is increasing, that means we're going uphill for values such that the derivative is greater than 0. This basically just means that the slope is positive. This is what we've known since Algebra 1. And f of x is decreasing for values of k such that f prime of k is, this is meant to be less than 0. That's a little typo here. So let me scratch that out. That's less than 0. And we call points where f of x is f prime of x is equal to 0, and again that's 0 slope, critical points. But we also say when f prime of x is undefined, undefined can mean you're dividing by 0, so that could be equal to infinity, or it's just simply you cannot figure it out. We also call that critical point. So I'll give you an example of an undefined point. So you may have a function like this, then all of a sudden you have this nasty corner here. And remember, functions are not differentiable if you have a corner. So at this point right here, this would be undefined. And we also call that a critical point. We call it critical because it is critical to knowing what the function looks like. Alright, so now we're going to talk about concavity. So remember before we found that inflection point, and we saw that before the inflection point it seemed like the function was the derivative was going down, 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 down. Then after the inflection point, the derivative was going up, 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 up. We say when the derivative is keep getting bigger and bigger and bigger, we call that concave up. And when you're actually looking at calculus, this will be when the second derivative is greater than 0. And the opposite, if you see the derivatives is going down, 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 then eventually negative, we call that concave down. And that's where the second derivative is less than 0. And we say that f of k is an inflection point if the second derivative is equal to 0. So we already said that. But I will show you guys this again in another graph. And once again, that relative maximum we saw, you would actually find that the relative maximum happens when the function is going from positive to negative. So this may seem kind of counterintuitive, but when you draw it, actually it's pretty easy to see. So you see the function here, the derivative here, the slopes are all positive, so here is positive, and then all of a sudden the derivatives are negative. And this makes the top of the hill, or your relative maximum. And then f of x is said to have a relative minimum when the derivative of f of x switches from negative to positive. So again, we're going from negative slope to positive slope. So how can we actually find a relative minimum or maximum if we're just given a formula and no graph? Well, it's actually quite easy. First thing you do is take the derivative of f of x. You set the derivative equal to 0. Remember, relative minimums and relative maximums always have 0 slope. And then you solve for x. And second, you need to find the second derivative. Now this is kind of backwards. So if the second derivative is less than 0, remember that's concave down, then you have a relative maximum. Well, it actually makes a lot of sense, because here the derivatives may be 5, then maybe 4, 3, 2, 1, 0, then negative 1, negative 2, negative 3. As you see, the derivative is going down, 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 down. And when the derivative is going down, you have concave down, which means the second derivative is less than 0. And exactly the opposite for relative minimum. With relative minimums, the second derivative is greater than 0. So here you see the derivative is just getting bigger and bigger. So we got like negative 5, negative 2, 0, 2, 5. So the derivative is getting bigger and bigger and bigger. So we call that concave up, and that's when you're going to have your relative minimum. And the one way I like to remember concave down and concave up is concave down looks like a frown, concave up is a smile, because you're feeling up. If the second derivative of x is equal to 0, which is called your inflection point, then the test is inconclusive. You really don't know if it's a minimum or maximum. In which case, you would just need to test the derivative before and after. So if you test the derivative and it's going from positive to negative, then you know that it is a maximum. If it's going from negative to positive, then you know it's a minimum. Okay, lovely. So here is an AP style problem. It is a little bit difficult, but follow with me and it probably won't seem too bad. So we're going to use a couple algebra tricks to solve this. So f of x is equal to x squared minus 1 over x cubed, and find the x coordinate of all critical points of f and determine whether each is a relative minimum or relative maximum. Okay, so we are trying to find the critical points. So remember, critical points are where the derivative is equal to 0 or where the derivative is undefined. So before I take the derivative of this function, I'm actually going to try and make it look a little bit simpler. And the way I can do that is I can actually split up the numerators. So we have x squared over x cubed minus 1 over x cubed. This is just a trick from algebra. And this is equal to, well, x squared over x cubed. That simplifies just down to 1 over x minus 1 over x cubed. And the reason this is so great is now I don't have to use the quotient rule, where before I would have had to use the quotient rule of this. So when I take the derivative here, well, I'm going to show you a little trick. When we want to take the derivative of 1 over x, well, 1 over x is equal to x to the negative 1, and then we take the derivative of that, we're going to have negative 1 times x to the negative 2. And then when we want to turn that back into a fraction, it's going to be 1 over x squared. The trick is you take the function, change the sign, so if it's positive, turn it into a negative, and then you raise the power of x. So we have f prime of x is equal to, like we showed before, negative 1 over x squared. And let's see if we can do the same trick with this other one. So we're going to turn that negative into a positive. So right now we're looking at this function here. We're going to turn that negative into a positive, and then of course we've got the 3, so we're going to put that 3 on top, just like normal differentiation. And instead of taking that 3 down to 2, we're going to bring that 3 up to a 4. Great, and that is the derivative. And we are interested at where the derivative is equal to 0. So this is equal to 0. So we have negative 1 over x squared plus 3 over x to the 4th. Okay. So now what we need to do is try and solve for x. So this is a little bit of a complicated problem. In order to make it a little bit simpler, I want to get rid of all these fractions, and the way I can do that is I can multiply each term by x to the 4th. So 0 times x to the 4th, then I've got x to the 4th times, that's a 4 right there, times negative 1 over x squared plus x to the 4th times 3 over x to the 4th. Now look at that, these x to the 4ths are going to cancel here. This x to the 4th and x squared are going to cancel down to x squared over 1. and I'm left with 0, because 0 times anything 0, is equal to negative x squared, so I still have that negative sign there, plus 3. Okay, now I need to solve for x. So I've got a pesky negative x squared again, so I'm going to do what I did before on the other problem, and I'm going to go ahead and move my work up to here now. I'm going to add x squared to both sides, so I get x squared is equal to 3. I'm going to square root both sides, and I get x is equal to plus or minus root 3. So these are two of my critical points, but I am not done. Remember, I have to see if anywhere if the derivative is undefined. But have a look at this function. Remember, if for something undefined, we often find if it's dividing by 0. So if I plug in 0 for x, then I have two undefined parts, so the whole thing is undefined. So f of x is f prime of x is undefined at x equals 0. So if I want to write all my critical points, let's go ahead and do this in a different color, as this is the answer. We have negative root 3, 0, and root 3 are all critical points. Great. But we also need to find out whether they're a relative minimum or relative maximum. So I'm going to go ahead and erase this ink off the slide and figure out when that's going to be. Okay. So just as a reminder, our critical points are negative root 3, 0, and then root 3. Now we need to find the second derivative now. So remember, f prime of x was equal to, oh gosh, what was it? It was negative 1 over x squared plus 3 over x to the 4th. That's what I get for erasing all the ink off the slide. Okay, so let's find the second derivative. So f double prime of x. We're going to use that same rule I taught you before. We're going to first deal with this guy. So we're going to change that negative to a positive. So this will be positive. And we're going to take that 2 up to the top. 2. And that x squared turns into x cubed. And we're going to do the same rule for this guy. So that positive is going to turn into a negative. And we're going to take 4 up on top. 3 times 4 is 12. And that's going to be over x to the 5th. So what we're going to do is we're going to plug in our critical points and find out if that second derivative is negative or positive. So all we need to do is figure out if it's negative or positive. Okay. So we have f double prime of negative root 3 is equal to, well, that's going to be positive 2 over, well, negative root 3 cubed. Well, root 3 times root 3 is just 3, so that would be x squared, but then we get a times by root 3 again. So this is actually equal to negative 3 times root 3. And here we're going to minus 12 over, well, it's x to the 5th. Well, x squared is 3, as we just shown. And then x to the 4th must be 9. So this is minus 12 over 9, and it's negative 9 root 3. So these two negatives become a positive. So this whole thing is equal to negative 2 over 3 root 3 plus 12. Oh, plus 12 over 9 root 3. Now we just need to figure out whether this is negative or positive. Well, 12 over 9 is bigger than 1, and 2 over 3 is less than 1. So a bigger positive and a smaller negative means the whole thing is positive. So the second derivative at this point is positive, and remember, if the second derivative is positive, we have a relative minimum. Remember, that's the tricky one. Sounds kind of backwards. You gotta trust me on this one. Okay, let's pick another color for the next bit. Let's do green. Okay, so now let's try plugging in some different points. So we already know that 0, f prime of 0 is undefined, but we'll also find that the second derivative at 0 is undefined, because 2 divided by 0 is undefined and 12 divided by 0 is undefined. So let's just go ahead and check f of root 3. F double prime of root 3, that is. So f double prime of positive root 3 is equal to, well, we're just going to plug in the exact same things like we did before, except the sign's going to be different. So we're going to get 2 over 3 root 3 minus 12 over 9 root 3. Now this time we have a bigger negative and a smaller positive, so the whole thing is going to be negative, which means we have a relative maximum. Now for the critical points where at 0, where the second derivative is undefined, what we're going to do is we're going to look at some points around 0. So let's try negative 1. So f double prime of negative 1 is equal to, well, 2 over negative 1 cubed is just 2 divided by negative 1, which is equal to negative 2, minus, well, x to the 5th, so negative 1 to the 5th is negative 1, so minus negative 12, so this becomes a plus 12, so that means the whole second derivative here is